Okay, so let us start with today's topics. So today we are going to see, first we will quickly recall the topics covered in the previous session, and then we will go to today's topics. Okay. So in the previous class, we saw how to calculate limits of scalar valued multivariable functions first, right? So for that, what we did, so for calculating the limits, this is the limit of, this is the definition for the limits of scalar valued multivariable functions. But particularly what we saw was how to use this definition to say that something does not have a limit. Okay, so to show that what we did, so we consider a function in, for example, if it is in two variables, then what we calculate the limit along different curves, like for example, along the x-axis, along y-axis, and then we considered y is equal to mx and so on, right? So we considered when y is 0 or x is 0. So any of these different curves we considered. So and we found what is the function's limit derivative, directional derivative along these three different curves. So if they are all same, then it is fine, and if it is not same, then we know that not same or does not exist, then we know that the limit does not exist. So mainly this concept we used to show that the limit of certain curve does not exist. Okay. And then for a vector value, it is quite simple. So suppose you are having something like e power x squared, and then here you have something like n sine 1 by n. Then you know that the limit of this multivariable, this vector valued function is that the limit of this particular, here maybe n squared, this particular sequence and this particular sequence separately will give you the limit of this vector valued sequence. Okay. And what is the continuity of a function? Am I audible?
Yes, ma'am.
Yes, ma'am.
Okay. So what is continuity of a function? If the limit of a function f from d to r, where d is a subset of rn, it exists at a point a1, a2, an. Okay. And the function value and the limiting value are the same, right? So limit x tilde going to a tilde, f of x tilde is equal to f of a tilde. Okay, so if this limit first of all exists and that limit is exactly equal to the function value, this is the function value. Okay, the limiting value and the function values should coincide. In that case, we call it to be a function, the function to be continuous at this point a tilde. It is exactly coinciding with the definition we see for one variable functions. Okay, fine. So, and the next thing is that how do we use gradient vector or a gradient function, and how does this is used for finding the directional derivative. So gradient vector is nothing but all the partial derivatives written as a vector. So for example, if it is just a function of two variables, then the corresponding gradient vector fx comma fy. So here it is the partial derivative with respect to x and partial derivative with respect to y is your gradient vector. Right? And if you have n variables, then you have to calculate the partial derivative with respect to n different coordinates. Okay, and this is the gradient function. And for a gradient vector at a particular point, you just evaluate the gradient partial derivatives at this a value. Each of this function you just evaluate and write the values. That's all. Okay. Anyway, this gradient vector or function is a vector. Okay, fine. And how are we using this to calculate the directional derivative? For a directional derivative, du of f, first of all at x is what? Del f of x tilde, let's say, del f of x tilde into the unit vector. So u is your unit vector. Remember, always for directional derivative, you should consider only the unit vector. Okay, you take the dot product. And for a specific point, you just replace this a tilde. That's all. Right? So this is the directional derivative in terms of the gradient function. All right? Okay. So today's topic, the first topic is that the direction of steepest ascent or steepest descent. What is the steepest ascent or steepest descent? So this problem here in the video which you have seen, There they have talked about the water flow, right? So either it can be for a water flow, or suppose a bicycle rider is riding on a mountain, so where it is very difficult or very easy for him. So such kind of similar questions are all addressing the same thing. What is the steepest ascent or descent? Okay. So in the example given in the video, you saw that so for an electrification project, you want to understand the water flow of a hill. Okay. So this is the outline of the hill given to you. Okay. So you want to find the direction in which the water is flowing. So you know that always the direction water flows in the downhill direction. So definitely water is going to flow in this direction, right? Here in this direction, and here like this. So you know this that the water flows in this direction. Okay, fine. But then this structure here is just representing an outline in the 2D, and that is not sufficient for a real problem. So what is that we are doing? We are considering this in the 3D direction. But before that, here what is given to you? The water flows depending on the direction of the slope. So here you consider this line. Is this a positive slope or negative slope? This line is having a positive or negative slope?
Positive.
Negative.
Positive.
See, as the value of x increases, your y value is also increasing. Then,
Positive.
yes, as x increases, your y is also increasing. So it means you are having a positive slope. Okay. So when you are having a positive slope, and water flow will be towards the left. And when you are having a negative slope, for negative slope, you see as the value of x is increasing, the value of y is reducing, right? As x increases, your y decreases. So this is a negative slope. So here the water will flow towards right. And here this is, what is this slope?
0.
Yeah, this is having a zero slope. There is no change in the value of y as x increases. So as x increases, y remains constant. So there the slope is 0. It means here the water is stagnant. It does not go down right or left. It does just stays wherever it is. Okay, fine. So this is what is given here. So what he thinks, he can calculate the derivative. So the derivative gives the slope, right? So from that, depending on whether it is positive, negative, or 0, he can judge what is the direction of the water flow. So if it is negative, the water flows towards the right, right? So that is what we saw here. If it is negative, the water flows towards the right. And if it is positive, it flows towards the left, and it is 0, it is remaining stationary. So this is what he is thinking. But then a friend suggests that a 2D structure is not sufficient. You need a 3D figure like this. Okay, so now you have a structure of a hill. So the water can flow in this direction, in this, or this, or this. There are several directions, several possibilities in which the water can flow. And to identify the direction in which it is flowing, what is the concept we are going to use? We are going to use the concept of directional derivative. Okay, so how to find in which direction the water is flowing very fast? Okay, so for that, you have to find the directional derivative. Okay, and then you have to find such that the absolute value among those for which it has a negative sign. It means what? You have to find a vector u in which the directional derivative is largest in the absolute value. So it means what? For example, you have, just I'm giving some values, -5, -3, -7, 7, 8, 9. So which one is having a largest absolute value here? Which numbers here is having the largest absolute value?
-9.
So this is the one having largest absolute value, right? Okay, so this is one thing. And also your HU, the directional derivative, should also be of the negative sign. Then only the water flow is there. Otherwise, if it is positive, the slope, then the water flow is not there. So you are considering the negative slope. Okay. So here they are considering the value for which the absolute value is largest, and also the sign of the directional derivative is negative. Okay. So how is the problem exactly done? Let us see next. In what direction is the directional derivative minimized? Okay. So for such a problem, let us say you are having a function on n variables. Okay. So f is from domain D to R. Here D is a subset of R and it is a scalar valued function. Okay. And you are considering a point A in D which is having an open ball around it. Okay. Now suppose you know that the gradient function exists and is continuous on open ball around A till. Okay. So this assumption is usually made. Most of the functions we are considering, it usually has, except for very specific problems which we are discussing in the class. Okay. So you see what happens here. Okay. So now what is the formula for directional derivatives in terms of gradient? Can you tell? Fu is equal to
Gradient into unit
Uh,
vector.
U vector by norm U.
Unit vector.
into u, right? So the gradient into the unit vector. So this is the directional derivative at A tilde in the direction of u, right? So now what is the formula for the dot product? If you know
Cos
the angle between A and B is theta,
A modulus of A and modulus of cos theta.
norm A,
Norm B cos theta.
yeah, right? So this is the formula we are going to use here. So if we are using this formula, then you get norm del f of A tilde into norm u into cos theta. Here what is theta? Here,
Angle.
yeah, theta is the angle between which vectors?
The gradient and the
The gradient and u.
Vector.
Okay. So now note that here u is a unit vector. If u is a unit vector, then what is its norm?
1.
1.
So you see that here norm u can be replaced with 1. Okay. So now your fu of A tilde reduces to del f of A tilde into cos theta. Okay. So given an f, for a given f, your norm del f of A tilde is fixed, right?
Yeah.
So depending on u, what is the only thing which changes in this expression? Depending on u, theta varies, right? So theta is the variable here. Now let us look at the graph of cos theta. This is the graph of cos theta. So let us consider it between 0 to 2 pi. Okay. Now look at this graph and tell me at which point the graph is having the least value. So you see that the graph is completely between -1 and 1. The graph is completely between 1. All the values are completely lying between 1 and -1. Right? So tell me at which point you have the least value. What is the least value that cos function is taking?
-1.
-1, and it is at pi. So at pi, the value of the function is -1. And also when it is taking the maximum value,
Like 0 or like 2 pi.
yeah, so we take the value 0 here. So you see that 0, it is 1. And then it is a periodic function. So at 2 pi, at 3 pi, so all these places, it is going to be again 2 pi and 4 pi and all these values. Every 2 pi distance, it is going to be again 1. Right? Fine. So here you see that cos theta is minimum when theta is equal to
Pi.
pi. Right? So cos pi is equal to -1. And cos theta is maximum when
Theta
theta is equal to zero. So what is cos zero? What is cos zero?
1.
1.
All right. Okay. Fine. So if you are drawing a tangent at this point, so the direction, the tangent at this point is nothing but the line parallel to
X-axis.
X-axis.
Parallel
okay.
to the
And
gradient.
here it is parallel to, here also it is parallel to x-axis. Okay. So you are having the maximum and minimum here. Okay. Fine. Now let us now come back to this expression fu of a tilde. What we wanted to find? We wanted to find the direction in which the minimum value is attained. So we already know that this function is now varying depending on the value of theta. So can you tell when does the function attain minimum value?
It's in the opposite direction of the gradient.
Yeah. So minimum value of fu of a tilde is attained when theta is equal to pi. So theta is equal to pi means what is happening? Suppose you are having, this is the vector del f of a tilde. Okay. So you should have 180 degrees. Pi is 180, right? At
U.
which you are having the vector u. It means what? U is nothing but the in the direction opposite to del f. Right? It means what? U is in the direction opposite to del f of a tilde. Is that correct? Right?
Yes.
If it is making an angle pi, it is in the direction opposite to del f. Okay. So they both are lying on the same line. So how can we define u? You know that u is a unit vector. Okay. And it is in the opposite direction. So you can write it as u is equal to minus del f of a tilde because it is in the opposite direction. And since it is a unit norm, you have to consider it divided by the gradient. Okay, fine. So this is the u where for fu of a tilde is attaining its minimum value. Okay, so in that case, what is the value of fu of a? So you know that when theta is equal to pi, what is the value of cos theta?
-1.
Minus 1. So the value is minus norm del f of a tilde. So the minimum is attained at this point u, and the value minimum value is minus norm del f of a tilde. Okay. Same way we can tell what is the maximum value. So maximum value
Will be del
of
f of 80.
yeah
No, del f.
is attained when theta is equal to
0.
0 degree.
0. So it means what? Both del f of a tilde and u are on the same direction. So both of them are in the same direction. Suppose if this is your del f of a tilde, so this your u is also in the same direction. Okay, both are in the same direction, but remember u is a unit vector, so we have to consider the division by its norm. Okay, so in this case, what is the value of your fu directional derivative? It is exactly norm.
No,
F of
del f.
80.
Okay, fine. So now, when does it remain unchanged? So when do you have a slope 0? Or sorry, when do you have cos theta value to be 0?
Cos 9.
Yeah.
9.
So it remains unchanged.
While theta is 90 degree.
Yeah. When fu of a tilde is equal to 0, which happens at 90 degrees here. Okay. Also here also it is happening. Okay. So at this point, you see that the value cos theta is becoming 0. Okay. As this point as well as here, the value is becoming 0. Okay. Fine. So here theta is pi by 2, comma. So here it means what? What is mean by pi by 2? It means when theta is equal to pi by 2 means we are considering when,
Perpendicular.
yeah, it is kind of perpendicular. Theta is pi by 2 means we are considering the perpendicular direction. Okay, it is perpendicular to the direction of the vector del f of t. So if this is, let me write it in green. So this is del f of a tilde, then this is your direction pi by 2. And here if it is in this direction, then it is 3 pi by 2 actually. Okay, so anyway, it is a perpendicular vector. That is what we need to understand. Okay, so here if we are considering only the range of 0 to pi, okay, then you have the vectors 0 where it is having the maximum, pi by 2 where it is having the where it is having no change, and pi where it is attaining the minimum value. Okay, fine. So this is what is given to you. So you have the
Ma'am, in this case, what is the minimum and maximum value represent? Like it's like the derivative, the slope is maximum and minimum at that point.
see maximum and minimum. What does it represents? So here, look at this. For example, in 2D, it is easy to understand. What does it mean? When the steep is maximum, okay, when the steep is maximum, okay, it means what? The water flows with greatest force. Okay, when the steep is maximum, the water is flowing with greatest force, and it is in this direction. Suppose it is in this direction, and the steep is maximum, then you see that here the water, if you are moving in this direction also, the steep is maximum means the water is flowing maximum. So steepest descent means what? Flowing down, downward flow. Okay, and ascent means upward flow. So ascent means upward direction. Suppose you are climbing, okay, so that is ascent means upward direction.
Ma'am, if I may point on this in this hill, and there can be both of the conditions simultaneously, right? It can be like maximum and minimum.
See, this point is the point where there is no change. It is
No,
having a zero slope.
if I'm in between the point, like you draw a blue line here,
Somewhere
like
here.
yeah, here there can be both. Like if I go upward, then it can be uh, like both minimum and
So
maximum.
here we are considering the flow of water. Okay, so flow of water we are considering from top to bottom. Suppose you are considering the flow of, let us say you are riding a bicycle from this point to this point, then you have to consider what is the ascent here and what is the descent here, and then what is the ascent and what is the descent. It depends on what is the problem you are considering. Okay.
So for general, what will say?
See, in this problem, mainly we are looking at the descent always, because the rain is going to pour in this way. Okay, so you are always considering only the descent in any direction. And suppose you are considering some other problem, as I told you, the riding of a bicycle. Then you are considering here, you are considering ascent, here you are considering descent, and here again ascent, and so on. So it depends on the question you are considering. So for example, here what is that they are considering? We have to find the direction in which h decreases fastest, or equivalently the rate of decrease of h is fastest. So for this, what they are considering, the directional derivative hu is largest in absolute value. So the absolute value of hu must be the largest. Okay, so that is what they are
So
particularly.
we have been asking that particular question that we want to find minimum or maximum value. Like we want to decrease
It is for a
ascent and
general
descent.
function. It is for a general function. This, whatever we are considering here, it is for a general function. For this particular problem, the description is above, and whatever we are doing here, it is for any problem, any function f. Okay. We'll do some examples so that you can understand. See here, steepest ascent. When you have the steepest ascent, when your fu is positive and f is maximum. See, in the case of 2D, for example, you are having some curve like this. Okay, see, there is an ascent here and there is an ascent here as well. But which one is steepest, you can easily identify, right? Which one is steepest? Suppose you are, imagine riding a bicycle.
The
Which
first
one will
one.
be
First
having
one.
more difficulty?
First one, madam.
right? Here you are having the steepest ascent. Okay. Same way, suppose you are having another curve. Let's say you are having something like this. Okay. So you are having a descent here and then you are having a descent here. So which one is steepest now in comparing these two?
Second
one.
Second one. So that is the meaning of steepest ascent and steepest descent. Okay. Fine. And no change means there is no change in the, so your FU is just 0. Okay, so here FU is positive and maximum, here FU is negative and minimum, and FU is 0 here. Okay, and whatever we have discussed here is this concept is for a general function f. So we will apply the same concept for different f here. So for example, if your f of x comma y is sine of x comma y, okay, you have to use this same concept given here. Okay, find the direction of steepest ascent. Yeah.
Sorry to interrupt, man. Just a doubt here. So, in this case, like no change. If I'm comparing it with the, the example that Sir used to say, the hill, those things. So it's the plateau on top of the hill, right?
Yeah.
The pond on top of the hill, like.
Yeah.
So, the unit vector in which direction would be the unit vector in? So it's 90-degree in the sense it must be in the y direction, right?
See, orthogonal to the gradient function. You are not considering the actual original function itself. You are considering the gradient
Oh,
function.
okay,
Please
fine.
keep that in mind.
Okay. Got it. Thank you.
Okay, fine. Okay, so for this, you have to now find the direction of the steepest ascent or steepest descent and the direction in which the function remains the same. So you have to find all these three things for this function. So first of all, you need to find the value of del f. So what is del f of x comma y for this function? What is the derivative of this function with respect to x? We have already done this. Y times of?
Cos xy.
Cos xy.
And what is the derivative of this function with respect to y?
X times of
Cos xy.
cos xy.
Okay, fine. Now at the point pi comma 1. So del pi of pi comma 1. What is the value? 1
1
cos pi
Cos pi.
comma
pi cos pi.
pi cos pi. What is the value of cos pi?
-1.
-1.
Okay, so this is the value of del f. Now for steepest ascent, what is the u?
Del f by norm del f.
So what is the norm del f of minus pi comma 1?
Root of pi square plus 1.
Root of 1 plus pi square.
Pi square.
Okay, so this is nothing but -1 comma minus pi
Minus pi.
whole divided by 1
Root
plus
of 1
pi
plus pi
square.
square.
Okay, suppose you are considering the steepest descent. Then
Minus del f by norm del f.
u is equal to minus del f by norm del f, which is minus
one-
of this vector will be
1
just
pi.
1 comma pi by square
Root
root of
1
1 plus
pi
pi.
square.
Okay, and where there is no change, for
0.
that you have to
0.
find, you have to find where the vector is orthogonal to this. So you need fu to be 0. It means what? You need to find a vector which is orthogonal to this. So it means -1 comma minus pi into x comma y equal to 0, which gives you minus x minus pi y equal to 0. So x is equal to minus pi y. So in this case, suppose you are taking your y value is equal to 1, then what is your x value? If y is equal to 1, x is equal to
minus pi.
Minus
Minus pi.
minus pi. So minus pi comma 1. And you have to consider the, remember you should always consider the unit vector. Okay, you see that this is orthogonal to this vector del pi of pi comma 1. So you just multiply and see the first -1 into minus pi is pi. So pi minus pi is 0. So you see these two vectors are orthogonal.
Ma'am?
Yeah.
Here x comma y denotes unit vector, right?
Yeah.
Okay.
See, x comma y does not denote a unit vector. If you want to consider a unit vector, then you have to divide it by square root of x squared plus y squared. You need to consider. So first we are finding the orthogonal vector to this, and then we are normalizing it. Okay, directly x comma y is not the unit vector. You are normalizing it to get a unit vector. Okay.
Ma'am, here value of y depends on x. It means there may be multiple value of x, y, orthogonal vector, I mean to say.
Yeah, maybe depending on your y value, you can also take a different x value, right? But the unit vector is finally going to be the same because it is along the same line.
Yeah.
Okay.
Okay.
Fine. Okay. So the same problem we are going to do for a different function. So now what is del f of x comma y comma z for this function?
2x I cap plus 2y j cap 2z.
Okay. So this is your del f. Okay. Now what is the direction given to you? I did not mention the direction. What is the direction? Just let me check. The direction is 1 comma 1 comma 1. Okay. So sorry, not direction, the point. So del f at 1 comma 1 comma 1 is 2 comma 2 comma 2. Okay. Now you want to find what is the norm of this vector. What is the norm of this vector? Square root of 12, right?
Yeah.
2 squared into 12, so which is 2 root 3, correct?
Yeah.
Now you see that what is the steepest ascent?
So u will be equal to
Del f by norm.
2x comma 2y comma 2z
So
by
1 by root 3, 1 by root 3, 1 by
1
root,
by yeah.
right? And steepest descent.
Minus 1 by root 3 minus 1 by root 3 minus 1 by root 3.
And then remains unchanged. When your u is orthogonal to this vector 2 by root 3, 2 comma 2 comma 2. So 2 comma 2 comma 2 dot x comma y comma z will give you 2x plus 2y plus 2z. It means what? Your x plus y plus z is equal to 0. So here remember, please everyone listen carefully. Here in this case, you are considering all the vectors x comma y comma z in R3 such that x plus y plus z equal to 0. Now what is this representing? In the previous case, it was just a vector. Okay, it was just a line, or you can say. Here you are having a set like this. What does this represent?
Plane.
Plane.
Okay, so this is representing a plane. So for a plane, how many vectors you need to define a plane?
2
Linearly independent vectors?
2 vectors.
2 vectors. So in this case, you need to consider 2 unit vectors. Okay, you have to find 2 unit vectors which are orthogonal to this vector 2 comma 2 comma 2. Okay, so here for example, x comma y comma x plus y plus z is equal to 0. So what are the vectors which are satisfying this condition x plus y plus z equal to 0? Any 2 vectors which are linearly independent?
1 0 minus 1.
1 0 minus 1,
1 minus
1 0. Okay, these 2 vectors we can consider, right? Okay, what are the corresponding unit vectors? You have to remember 1 by root 2, 1 0 minus 1, 1 by root 2, 1 minus 1 0. Okay, so along this both these directions you will have fu equal to 0. Okay, is this fine here what I told you? Fine. So here the steepest ascent and steepest descent may also be asked as direction in which f is increasing fast. Okay, here it is decreasing fast. Okay. Here no change. Direction in which there is no change in it. Okay. So this is the this is how we are using this concept of finding the steepest ascent and steepest descent. Okay.
Ma'am, is there
And
any way to look at it in a graph form?
sorry.
Is there any way to look at it in the graph form and verify this?
I guess it is there in sir's video itself, I guess.
No, there
I don't know
isn't a software.
specifically any gap I have included in this particular video. Maybe I will check. I guess I saw something in sir's video. If not, I can give you some specific picture in the next class. Maybe this place where I have not included anything specific, but I can add it if you want. Okay.
Ma'am,
Ma'am, is there a website where we can look at the...
Website, I don't know anything specific. Sorry.
Okay, ma'am. Thank you.
Okay.
yeah, ma'am.
Fine.
Small doubt. In that unit vector which you chose for x plus y plus z equal to 0, you can also choose 2, 1, minus 1, right? Sorry, 2, minus 1, minus 1. So that won't be unique, right? So how
2
can
minus 1 minus 1. Yes, they are not unique. Of course, they are not unique. But you see the unit vectors, whatever unit vectors you are considering, they will be finally anyway almost similar, or you can equate. See, in this case, unit vectors need not be similar as well because you are going to get different things. Yeah, it is fine.
They will be on the
As long
same
as you are
plane.
able to find any two linearly independent vectors which are orthogonal, it is completely fine. You don't have to worry about the uniqueness. Okay.
They will all be on the same plane, that's all, right? Like,
Sorry.
they will all be on the same plane, but they can be different. Like,
Yes, there
in
can
the
be different.
correct.
See, even R2 itself, you can consider these two vectors or these two vectors as a basis, or these two. There are infinite number of choices which can span the same plane. The same way, for any plane, it is possible to take any two different vectors which is spanning that set. Okay?
Okay, ma'am, thank you.
Okay, fine. Okay. So here in these cases, we were able to find the steepest ascent and steepest descent. But it is not possible that for any given function, you can find the steepest ascent and steepest descent. Why? We have already discussed certain examples where the directional derivative does not exist. Right? For example, this particular example, we know that at 0, 0, you know that the directional derivative does not exist. It exists only in the direction of x-axis and y-axis, right? So in general, it does not exist. So you cannot apply the above technique for this kind of functions. Okay, for using for finding ascent or descent at a point for 0, 0, this function we cannot use the above method. Okay, because here you know the directional derivative does not exist. Okay, fine. Okay, so tangents, next topic is tangent. So what is the first topic we have seen? Steepest ascent or descent. For this is the main table you need to remember. Okay, this is the main table you need to remember for steepest ascent or steepest descent. And this term can be asked in different ways. For example, I told you, right? What is the fastest direction, direction in which there is f is increasing fast. Okay, so there can be various ways in which the same concept can be asked. Okay, so the next concept is tangents.
Ma'am, just one second, ma'am.
Hmm.
On the above question where you said in the direction, so that actually gives the point, right? It gives the coordinates of the point, but
Yeah.
but how does it give the direction? It is that point on which the ascent is the fastest or the lowest, right? But how does it when you say direction in which f is increasing the fastest, the coordinates are of a point, right?
Exactly, it is the coordinates of a particular point you are considering, and you are considering, see, you are considering the steepest ascent or steepest descent. So first, ascent or descent means you are considering the directional derivative. So directional derivative, let's go back. What are directional derivatives? Directional derivatives are like you are considering the derivatives in some specific directions, right? There can be numerous directions and some specific direction you are considering for directional derivative, right?
Yes,
So
yes.
remember, what are partial derivatives? Partial derivatives are directions only along x and y axis, right? But what are directional derivatives? These are derivatives along any given direction. So that particular direction we are finding by this vector u. Okay. So remember, in the case of one variable, what we do, we simply find what is f dash of x, and that gives you the vector. So the same concept here we are doing. Instead of your derivative, here you are using the directional derivative. That is the only thing we are doing. No other changes done. Okay. Fine. Okay. So what are tangents? First, we'll recall whatever you have seen for the one variable case. So in the one variable case, suppose you are having a curve like this, then you know at this point a tangent is something which is touching
Just
this
touches
point
that
like this.
point.
Okay, so it is just touching this line at the line like this, touching the curve like this. Okay, so tangent also tells the slope at that particular point. Okay, fine. So you see a tangent line to a curve C at a point P is a line which represents the instantaneous direction in which the curve C moves at a point. So suppose you are having a tangent line like this. Now you know that the direction of the slope is moving in which direction? Towards the right. So the slope is like this. Okay, it tells you the instantaneous direction in which the curve is moving. Okay. Also, we usually say the line which exactly touches the point at a curve. Okay. Okay, fine. So, for example, you consider this y is equal to x cube. So, these are all the different tangents. But what is a tangent at the point x is equal to 0? Can you tell? For this particular curve, y is equal to x cube. What is the tangent at x is equal to 0?
X equal
x-axis.
0. Y equal to 0. Y equal to 0. X-axis.
So, it
X-axis.
is this. Right? This is
Yeah.
the tangent at x is equal to 0. Right? So you see that now it is not just touching the curve, it is cutting the curve. Okay, so we cannot stick to this traditional definition. This varies depending on whatever curve and the point we are considering. For the other points, it seems that the definition here is matching, but for this point, it is actually cutting the curve, not just touching the curve. And you know that the equation for finding a tangent is given by this: y is equal to f of a, y minus f of a equal to f dash of a into x minus a. And what does this f dash of a represent?
Derivative of
Yeah, it is the derivative of a. So it is the
point A.
Slope.
slope.
Yeah, slope of the tangent line, right? It is the slope of the tangent line. Okay, fine. So now, with this in mind, let us look at what are tangents for f of x comma y. First, let us look at functions of two variables. Then we will generalize it for n variables. Okay. So let f of x comma y be a function. Okay, on a domain D in R2 containing some open ball around the point A tilde. Okay, so for example, we are considering this function, this surface you see here in purple color, that is a function f of x comma y I am considering. Okay, this is your f of x comma y. Okay, graph of f of x comma y. Okay, and it is a surface you see. Now consider a plane in D passing through A tilde and restrict f to L. So this is the plane. So this is your A tilde. This yellow point is your A tilde. Maybe I use a different color. This yellow point is your A tilde. And you are considering this is the plane through F A tilde. Okay, you are considering a plane passing through this A tilde. And what you are going to do, you are going to restrict this function. So this is your F, right? You are going to restrict this F on this plane. So if you are restricting this function on the plane, then what is that you are getting? This black color curve you see, right? So this is the restriction of f on the plane, correct? So this is the restriction of this function f on this plane. Okay. Now you see that it is now just a function of one variable. So it is simply it is a simple curve. It is just a function of one variable. Okay. Now we consider the tangent of f at A tilde over L as in the previous slide. So in the previous slide, how we define? So we have a curve like this, and how do we define tangent? The same way we are considering. Okay. So if the tangent L is in the direction of the unit vector u, then the tangent will be the line. If the tangent is not L, if the tangent is in the direction of the unit vector u, then the tangent will be the line with slope fu of A tilde. Here earlier, what is that we consider in one dimension? F dash of A with slope f dash of A. Analogous. What is the analog in one variable case I'm writing? Okay, and what is the point it is passing through? It is passing through f of A comma f of A, and here it is passing through A tilde comma f of A.
F of A.
Okay, so you see that it is just very analogous to whatever we have seen in the case of 2D. Okay, so this is in a particular direction of the unit vector u. Okay, so this plane is now passing through this unit vector u. Okay, so fine. So what is the formula to find? There are various, in the case of one variable, there is one specific formula you have, but here there are various forms in which you can write the equation of a tangent line. This is the one we are commonly using. Parametric equation, or it is almost vector form and parametric are almost the same. Just return it with some splitting. They are almost the same. This is the one we are commonly using. Okay, so let f of x comma y be a function defined on a domain D in R2 containing some open ball around a comma b. So the equations of the tangent line to the function f at the point a comma b in the direction of the unit vector u1 comma u2 is given by the first 2 points a and b are remaining same. And what is this f of a comma b? The third coordinate here. Sorry.
U1z function, right, ma'am?
Sorry. The z of t. So your z of t is nothing but f of a comma b plus t times of fu of a comma b. So this is the parametric equation you are obtaining. Okay. So here, if you remember this or this, whatever is convenient for you, both are actually the same. You can find the parametric equation of a tangent for a given function at a point. Okay. So for example, let's look at this. Yeah.
If we do the y minus that equation, y minus y0 equal to m into x minus x0, if we try that for this, we will get the tangent plane, right? Not the tangent line, and this is like
that is coming next. No, that is coming next. Okay.
Okay.
We'll do that next. So first we have to find this x of t, y of t, z of t. Now for this, what is your a comma b? First of all, you should note what is your a comma b at whichever point is, that is your a comma b. And what is u1, u2? It is the direction of the unit vector. Here the vector is already in unit vector, so straight away we can take it as u1, u2. Okay. So ab is given, u1, u2 is given. So what is x of t then? X of t is a plus b u1. So 1 plus t. And what is y of t?
1 plus
B.
1.
1 plus 0.
0,
Right? So it is simply 1. And for the third coordinate, you need to find the directional derivative at the point. So let's find the directional derivative. So for that, first let's find the gradient. What is the gradient?
Y,
it is simply 1 comma 1.
Yeah, 1.
Right? And so for any point also it is going to be the same. And your unit vector is here. So what is your fu at 1 comma 1? It is 1 comma 1 dot 1 comma 0, which is 1 plus 0, 1. Okay. So now what is f of a comma b? A comma b is 1 comma 1. What is f of 1 comma 1? 2. Right? So your z of t is f of a comma b plus t times of fu of a comma b. So 2 plus t. Is it fine? Is it fine? Do you all understand here up to this?
Ma'am,
How did f of 1 comma 1 become 2?
See, what is f of 1 comma 1? 1 plus 1.
Oh, okay. So fu of 1 comma was for 1 point, right?
Yeah.
Okay, got it.
Okay. Fine. The same we have to do here as well. So what is x of t, y of t, and z of t? So first we will write what is your a, b. Here, is this a unit vector?
No, ma'am.
No.
So we have to find what is the unit vector. What is the unit vector here?
3 by 5,
3
4
by
by 5.
root of uh,
3 by 5, 4 by 5.
5. Okay, 25.
Okay. So this is your u1 and this is your u2. So we will go back to the formula. X of t is a plus tu1. So 1 plus 3t by 5.
5.
And b plus tu2.
40 by 5.
Okay. And for the other part, we need to find the directional derivative. So what is del f of x comma y?
Y comma x.
And del f of 1 comma 1 is again
1
One
1
comma 1.
comma 1. So fu at 1 comma 1 is 1 comma 1 dot product with 3 by 5 comma 4 by 5, which is
7
3
by
by 5
3 by 5 comma
plus
4 by plus 4 by
4 by 5, which is 7
7
by
by
5.
5.
Okay. Now what is f of 1 comma 1? 1,
1.
right? 1 into 1 is 1. So let us put it here. F of 1 comma 1 plus t times of fu of 1 comma 1. So plus 7t by
7
5.
by 5.
Okay, is this fine? So this is the tangent equation of the tangent. Now what is f of
But
x?
ma'am, but ma'am, one second, ma'am. Can you go up, please? But but in this equation for the tangent, so this is giving the so so this has three coordinates, right?
Yes,
This has x, y, z, all three, right?
yes.
But our function was defined in R2, right?
See, that is what I told you in the very beginning of multivariable calculus. For a function of two variables, f of x comma y, okay? What? So the coordinates in 3D are your x, your y, and f of x comma y. These are the coordinates in the graph of the function of f of x comma y. So this is the function and this is the graph of the function. So
Okay.
your graph, for example, here, okay? So here, what is the graph saying? So you take a point here, okay, whatever the coordinates of x and y, and the third coordinates. So for example, in f from R to R also, you are considering a function of just one variable, right? Why you need R2 then? Why you need x and y axis? Your y axis is actually your f of x, right?
Yes.
Understand? The same
Yes, ma'am.
what is going on here also. Your third coordinate is nothing but f of x comma y. Okay?
So it's like a translation for z plus in the direction of that in the unit vector, change in that unit vector, right? Like
Yeah.
the tangent, yeah.
Yeah. Okay? Fine. So now you see f of x comma y equal to sine of xy. Now for this, what is x of t, y of t, z of t? Now this is your a, this is your b. And is this a unit vector?
No.
No.
No, ma'am.
What is a unit
1
vector
by
here?
1
1
root
by
5,
5.
2 by root
Root 5.
root 5.
Okay. So this is your u1, this is your u2. So now a plus tu1, so pi plus t by root 5, 1 plus 2t by root 5. And what is the directional derivative?
I cos xy, x cos y, xy.
Into
Which is
1 by root 5.
at the point pi comma 1 is
Minus pi.
Minus 1.
right, minus 1 comma minus 5. Okay. Now what is your fu at pi comma 1? So it is minus 1 comma minus 5 dot product with 1 by root 5 comma 2 by root 5. So what is the answer?
Minus 1 minus 2 pi by root 5.
Okay. And what is f of pi comma 1?
0.
Sin pi equal to 0.
Okay, so 0 plus t times of this. So you have minus 1 minus 2 pi by root 5 t. Okay, so this is your equation of the tangent. Oh yeah, so this whatever we have seen is for functions of two variables. The same can be extended for functions of n variable also. Suppose you are having a function of n variable, the same kind of parametric equation happens. So you have x1, x2, xn, x1 up to xn, and then the last one is your z. Okay, so here one variable is missing, f of x comma y comma z. So here, suppose you are having x, y, z, then what is the image? You have to use a different notation. Okay, maybe you can use x, fx, fy, sorry, yeah, fx, fy, fz, and the last one maybe you can use something like u. Okay, fine. Let's do it for the n-dimensional case. So in this case, the problem is as usual. Here it is now a1, a2, a3. And is this a unit vector?
No.
So what is the corresponding unit vector?
Minus 1 by 3 minus 2 by 3, 2 by 3.
So this is your u1, u2, u3. And the same formula we are going to write. Okay. What is your x of t, y of t, z of t, and u of t? Okay. So this u is just another variable different from x, y, z. Okay. That's all. No specific, don't confuse it with this unit vector. Maybe if it is confusing, we will put w. Okay. Let's put w of t. Okay. Just something different from this x, y, z. Okay. So now what is x of t? Ai plus tui. So which is a1 plus tu1. So 1 minus
1 minus t by 3 minus 2 minus 2 t by 3 2 plus 2 t by 3.
Minus
1 minus, sorry, 1 plus 2t by 3.
3.
Right? And for the last component, you need to find the directional derivation.
Directional derivation.
So what is del f of x comma y comma z?
It would be y plus z, x plus z, and x plus y.
Okay. And what is del f at 1 comma 1 comma 1?
2 comma 2 comma 2.
Okay. Now fu at 1 comma 1 comma 1 is nothing but 2 comma 2 comma 2 dot minus 1 by 3 minus 2 by 3 2 by 3,
2 by 3.
which is minus
Minus
2
2 by 3
minus 4
minus 4
plus 4
4
divided by 3, which is minus
2 by 3.
2 by 3. Okay. So here it is nothing but, okay, here one more thing. What is f of 1 comma 1 comma 1?
3.
3. So here it is 3 minus 2t by 3. So this is the last coordinate here. Okay, I guess there is,
But here,
yeah.
but if you look at this now here, so for something that had 3, now we are defining it with 4 coordinates, right?
Yes, yes.
But how will you in a 3D space? So now this is 4D.
4D we cannot visualize. Only up to 3D we can visualize. Okay. After 3 dimensions you cannot visualize, right?
Okay. So what does that mean? So every time there is, every time we are trying to define the point for a tangent, one coordinate will be more, right?
Yes. Yes.
Okay.
See, for example, in the case of just a scalar valued function itself, it is a function of one variable, and you are having a curve in 2D. Okay, and you are considering a point. The tangent is along the point a comma f of a, right?
Yes.
So the same is just going on as the dimension increases. It is going along the point a comma f of a, your tangent. The same is happening for any dimension.
But
okay?
why can't the coordinates of the tangent be defined in only if there are three, then only three in three.
So first of all, for tangents, you need the graph of the function, right? Always the graph will have an additional coordinate, right? Otherwise, the graph, how do you draw the graph if you don't have what is the function evaluated function value? The evaluated function value is contributing to the additional variable here, additional component here.
Okay.
Okay?
Okay.
Fine?
Fine, ma'am.
Okay. So where were we? Yeah. So just like we have already seen that directional derivatives does not exist at 0, 0 for this function except for the x and y axis direction. So in that, so for that we already saw the steepest ascent and steepest descent we cannot find using the method we have seen. So for the same reason, again we are saying the tangents at 0, 0 need not exist. Okay. So the same, like for example, in the case of R2, any function with a sharp edge, we see that the tangent need not exist, or a function with discontinuity, the tangent need not exist. Right? There are several possible cases where the tangent does not exist at a specific point, right? So the same kind of reason we have for the multivariable case also. So for functions, certain functions, the tangent need not exist. If the directional derivative is not existing, then the tangent will not exist. So in 2D, we know that for this point, the tangent will not exist. For this point, the tangent will not exist, right? The same way, here for this function, directional derivative at 0, 0 does not exist in all directions. So except there is this exception, right?
Except
So
always
always remember that except y-axis, x and y-axis. Okay. Therefore, tangents need not exist. Okay. And there is another example this time. F of x comma y is modulus of c. This is a very beautiful graph. So f of x comma y is mod x plus mod. Easy to understand, right? This curve helps us to easily understand. See what is happening in the 2D. We are easily able to see because there is a sharp edge. Exactly the same is going to happen in this kind of a function also. Now imagine a plane passing through any of this curve. Automatically when you are restricting the function, you are going to get this sharp edges, right? When you are going to cut this cut this surface using any plane, you are automatically going to get sharp edges at which the tangents are not going to be defined. Okay, so for this there are many points where the tangents are not going to exist. Okay, this is another example. So what is the condition under which we can say that the tangents exist? Okay, for that you need the gradient to exist, and also it should be continuous. First of all, the gradient should exist and it should be continuous on some open ball around the point A tilde. Okay, then for every unit vector, the directional derivative fu of A tilde exists and equals del f of A tilde dot u. Okay, so this is what they are saying for the existence of tangents. The same is the condition here also, right? So the same is the condition here also. Here, for example, what is the derivative of this function? Here the derivative, you see that the function is not continuous at the point. So for example, this is f of x is equal to x if x is greater equal to 0 and minus x is fx less than 0. So what is your f dash of x? F dash of x is 1 if x is greater equal to 0, minus 1 if x is less than 0. So at 1, you see the function is becoming discontinuous. So I am drawing the function of f dash here. So this is the function f, and f dash is up to, for greater equal to 0, it is 1. And for less than 0, it is minus 1. So at 0, this f dash is discontinuous, and that is why you see that here you don't have a tangent. Exactly the same reason they are saying here. You need the gradient, first of all, should exist, and also it should be continuous. Then the directional derivative exists. So in such cases, the tangents are also going to exist. That's all. Okay, everything is very analogous to the one-dimensional case. Okay, fine. Okay, so once we are now understanding what is tangent, then we need to understand what is a tangent plane. Why we need a tangent plane, not just a tangent? Because we are not in just 2D anymore, right? For example, consider this surface. Okay, so for this surface here, you see, for the same point, if you are considering a plane passing through this curve and then restricting it, then you see that this green line is one tangent. And then if you're considering another plane passing through the same point but in a different direction, then you are getting another tangent, right? So here particularly they are considering directions. Here you see the shadow below one. So this is kind of the plane pass which is parallel to x-axis. Here another one is parallel to y-axis they have considered. Just I'm just giving the details of this graph. Okay, so you see that there are two different tangents for this particular point. Okay, actually you can draw different curves and make many more tangents for this same point. Okay, so you see that there is going to be a plane which contains all these tangents for the particular point. Okay, that plane which contains all this tangent is called your tangent plane. So this is your tangent plane. Okay, by a plane you already know it. For a plane, how many vectors you need for defining the plane?
Two vectors.
So,
So they have here two vectors and they have considered a plane here. Okay, fine. So let f
But
of
ma'am,
x.
for a 3D, sorry ma'am, for a 3D, there can be also multiple planes, right?
that
Yeah,
tangent
again,
plane at a point will be one, right? Like at one point it will be one, right?
you are
Just
considering one particular point. Okay.
So on that, only one plane will exist, right?
Yes. Yes. Okay. Fine. Let f of x still be a function defined on domain D in Rn containing some open ball around the point. Suppose del f exists and is continuous on some open ball around the point A tilde, then the equation of the tangent plane to f at A tilde is given by this. Now you see that this is very analogous to the equation of the tangent in one variable, right? In one variable you have y is equal to f of A plus f dash of A into x minus a. You see, it is very analogous now. Here, remember, it is a dot product here. Okay, so now this gives you the equation of the tangent plane. Okay, let us see some examples for this. Now, f of x comma y is equal to x plus y. Now, it is tangent. What is a tangent at one? Tangent plane at 1 comma 1. We have already found the tangent. Now, we are going to find the tangent plane. So, what is the equation? Z is equal to f of a tilde plus del f of a tilde dot x tilde minus a tilde. Okay, so x tilde is something x comma y, and your a tilde is nothing but a1 a2. This is your a tilde. Okay, so for this first you need, what is your f of a tilde? What is f of a tilde?
two.
A tilde is 2. Okay, and what is your del f of x comma y is 1 comma 1, so del f of a tilde is also 1 comma 1. Now
I'm
what
not
is
able to get the
f2?
clear visuality here. Can you explain it again?
Which one? This equation?
No, this is the process. I got it, but how did we get this thing? Like, can you
The
explain it?
procedure of how we got this equation.
Yeah.
Okay, fine. So
Because
for
I watched the lecture, but I didn't get it. The clear visuality why we are doing this.
actually it involves some derivation. I have not included the
Yeah,
derivation
that
here.
the tangent line thing I also didn't get it. Like the,
Yeah, actually it is the dot product. Okay, so there whatever equation you have taken here, using that only they have derived this also. So
I also
using
didn't
this,
get this thing also. Why we are
okay. So you
using?
want the derivation part of how we got this, right?
Yeah, I have no
Okay, fine.
visuality. I can do the questions, but I have no visuality. Why we are
You want to understand it visually, like how this is happening here.
yeah, the thing the tangent line thing.
This equation, how we can visualize here? Is this what you are asking?
Yeah, and how we got that equation also.
Okay, so this okay, it is actually very difficult to explain it completely graphically. But if you want the derivation, definitely I can give you the derivation. Derivation, but exactly this part to match it here, because gradient vectors we cannot visualize just in the case of 2D. In 3D, gradient vectors are not very easy to visualize. So directly to understand it graphically is difficult. But definitely you can.
We can just
See the derivation part, I can give you that. Okay.
Yeah,
go
ma'am.
with analogous, right? Like in 2D, it will be like y minus y0 equal to m into x minus x0. Like the
Y
line it
minus y0 is
In
equal to
2D,
m into
x,
x
x
minus
minus
x0.
x0. This
Exactly
m,
something like you are saying here. It is the
yeah,
equation of a line passing through x naught comma y naught,
yeah.
right?
So exactly same one. When it's z, it will be z minus z0.
the
Z0
plane
will
thing I
be f
got
of
it, but in plane, it's like we can
See,
say, but
he's saying that what is this x naught, y naught, m, everything, it is kind of visualize, you can visualize in R2. He's saying that he's not able to visualize this in here.
Here the
And
x0,
that is
y0
difficult
will be
actually.
the A tilt, right? X0, y0 will be the A tilt. And what, so f of x0, y0 will be here whatever f of A tilt. So it will be same that way we can
Okay, fine. So I don't know whether you can have a very clear visualization. I have not seen any videos where they have exactly shown the visual description of this equation, but the derivation part I will provide it to you.
can you
Okay?
explain the derivation part of the above thing that you did in the tangent line process?
Oh, better I will provide the derivation to you separately, because if I'm doing the derivation here, I won't be able to complete it. Definitely, I will provide the derivation to you. Okay?
You can do it, ma'am, after the class.
After the class, okay. If the time is there, I'll do it. Okay. Otherwise, I
Okay.
will provide it, and if you have doubts, you can ask it during revision or anywhere after the class in the next time. Okay. Fine.
Okay.
Okay, let's not get disrupted. Let's continue with the flow, and all the doubts we will discuss at the end. Okay, please. It's okay if you are asking the doubts in this concept. It's completely okay. Fine. Yeah. So x tilde minus a tilde here is nothing but x tilde minus a tilde is x minus 1 and y minus 1. Okay. Now, if you are applying it to this formula, what is now del f of 1 comma 1 dot x minus a tilde, x tilde minus a tilde? What is the dot product of these two vectors?
It would be again x minus 1 and
It is x minus 1 plus y
y
minus 1.
minus 1.
So x plus y minus 2. So now what is your z? Your z is f of a tilde, which is 2 plus x plus y minus 2, which is x plus 5. So this is the equation of the tangent plane. Okay, for this function at 1 comma 1. Okay, the same way you can do for other functions also. So here again, what is your a is this, a tilde is this. Okay, and what is x tilde minus a tilde? X minus 1 comma y minus 1. And what is f of 1 comma 1? 1, right? So now z is equal to f of 1 comma 1 plus what is your del f at 1 comma 1? It is just 2, right? We have already derived this. Del f of x comma y is y plus x, and that is sorry, y comma x.
And
Yeah, so here it is 1 comma 1. Sorry, here it is 1 comma 1. Now the dot product of this with this is
1
x
plus 1,
minus 1 plus y
y
minus 1.
minus 1.
So it is x plus y minus 1. So z equal to x plus y minus 1 is the equation of the tangent plane for this example. Okay. And here again, what is f of 1 comma 0? Sine 0 is
0.
0, right? And what is your del f of x comma y? We already have computed it. Y cos xy
Cos xy.
x cos
X
xy.
cosine. Sorry, xy.
So you have del f at 1, 0 is 0, y coordinate is 0, so the first
0.
coordinate becomes 0, and the second coordinate here
1.
is 1 into cos 0, 1. 0, 1. Okay. Now, what is your, this is your a tilde. So, what is x tilde minus a tilde? X minus 1, y. And what is the dot product of this two? Del f of 1, 0 dot x tilde minus a tilde. It is x minus 1 into 0 is 0 plus y. Okay. So, your z is f of 1, 0, which is 0 plus y. So, z is equal to y. This is the equation of the tangent plane. Okay. Now, you are going to, now more than two variables also, the procedure is exactly the same. Okay. So, now this is your a tilde. So, what is x tilde minus a tilde this time? What is your x tilde minus a tilde this time? X minus 1, y minus 1, and z minus 1. Right? This is your a tilde. Now, what is f of 1, 1, 1?
3.
3.
3. Right? Now, what is del f of x, y, z? Y plus z,
That would be
x
y
plus
plus z,
z,
x plus
and x plus
and
y. So, del f of 1, 1. I'm doing
2,
it fast because these things we are repeatedly doing.
2, 2.
Okay, doing calculation faster is not a problem, I guess. Concepts I will go slowly. Okay,
Okay.
x tilde minus a tilde, here it is equal to,
Sorry, madam. How did we got
how did we get what?
this y plus z and x plus z and x plus y?
Partial
Partial
derivative.
derivatives, right? Fx, fy, fz.
Oh, okay. Thank you, madam.
Yeah. 2 times of y minus 1 plus 2 times of z minus 1. So this is 2x plus 2y plus 2z minus 3. Sorry, minus 6. Minus 2, right? Okay. And here you have a 3. So f of 1, 1 and del f of 1, 1, 1. Okay. So you have here, since z coordinate is already here, maybe I will take something like a w, which is 3 plus 2x plus 2y plus 2z minus 6, which is 2x plus 2y plus 2z minus 3. See, now it is not a plane anymore. Now it is something having a dimension more. So now it is a hyperplane. So you see now for a tangent, when you are having 4 coordinates, then you are having a 3D structure. Okay, fine. So the same thing you can do here. I guess this kind of problem you are very familiar. I don't want to do the same calculations again and again. It is okay? Shall I leave this as a homework? This problem? Or should I do this?
Yes, ma'am.
You can leave it as
Yes,
Homework.
ma'am.
Just one thing I want to say, that there was some calculation error for this calculation in the video. Okay, so in that calculation error, I guess f of 2, 3, 1, it was taken as 3, but here it is not 3. So f of 2, 3, minus 1 is 4 plus 9 plus 1 is 14. So because of this, there is some calculation error in the video. So please note that. Don't take the same answer from the video. Okay, so look at this calculation error and do it. Okay, so linear approximations are exactly the same concept of tangents, just the name is different. Okay, so I guess in the sir's video also, sir has mentioned about the gradient descent concept.
Excuse me, ma'am.
Yeah.
Ma'am, I didn't get the part of hyperplane.
I thought I will include the slides here, but
No, ma'am. No, that hyperplane part. How it became hyperplane?
see Here for up to 2 variables, it is just a tangent, it is just a plane. Now for when you come to n dimensions, you are now having more than x, y, 2 variables. So if you know that x plus y plus z is equal to 0 or c, now this is the equation of a plane. Now only when you have 3 variables, it is a plane. Now when you are having another variable, or you can have for x1, x2, xn, any number of variables you can have. So whenever you are having this many variables, then you see that using this concept, actually Sir has explained in the video here, what is the exact hyperplane coinciding with this? Where is that expression? Sorry. Yeah. So using this part, actually Sir has explained that with this part, you can actually find what is the hyperplane related to it. So for example, this will be the part which is providing the hyperplane for this case, and when its dimension is also increasing, this is the part which will be describing the hyperplane, the last coordinate, not the z, but remember z represents the function evaluated value. So this part is actually contributing to the hyperplane. So here also you see that the dimension has increased, and that contributes to a hyperplane. Okay, so
Hyperplane is essentially one dimension less, right? Whatever the function we are doing, the tangent
yes,
plane is one dimension less than that, right?
exactly. Okay, fine. So yeah, linear approximations are nothing new. So there is nothing new you are going to learn in linear approximation. Just that understand that tangents are the linear approximation. Tangents or the tangent planes or hyperplanes, these are the linear approximations you see. They are not nothing new. So you see f of a tilde plus del f of a tilde dot x tilde minus a tilde. So this is the linear approximation we are saying. That's all. Okay. So you are having different curves. Okay, in 3D, in 2D, or whatever. Okay. All these different curves, when you are linearizing it, for example, in 2D, you are finding a linear approximation with a line. Okay. And in 3D, you are making a linear approximation with a plane. And in when the dimensions are increasing, you are finding a linear approximation using a hyperplane. Okay, so linear in the sense that the equations are of the form a1 x1 plus a b or a n xn equal to some y or something like this. Okay, maybe I'll write b here. Okay, so you are going to have some equation of this form. So they are linear equations. Okay, so linear approximations are nothing but the tangent planes or hyperplanes, which we have just seen earlier, which is given by this. So here the calculations are exactly the same for f of x comma y equal to xy. This exact problem I have done here already. Z equal to x plus y minus 1. That is the exact same answer here as well. It is not new. And for the next example also, it is going to be exactly the same, which I given you as a homework. Okay, so linear approximations are nothing but the corresponding tangent planes.
In 2D, when we calculate tangent, we are essentially doing linear approximation, right? Like we are
Exactly.
Yeah. So
Okay.
the
So
same
literally,
idea
it's just
here
a
also.
different name.
Sorry.
Sorry, just yeah, cool.
Like it's a process. Like we are at that curve at that point, we are estimating it to a line. If it's a line,
Exactly.
yeah.
Exactly. Okay, so this linear approximations, for example, yeah, before that I wanted to say that in Sir's video, Sir has mentioned why the concept of gradients are important, right? In the machine learning technique, there is a concept of gradient descent. Okay, the word descent itself says that the gradient, you are going to do some descent value. So when you are having curve like this, you want to find the steepest point. So for that, they have a mechanism called gradient descent, where this concept of gradient is going to be useful. That is why these gradient concepts are told it is very important for machine learning. Same way, linear approximations, you see in linear regression, what is done is exactly linear approximations. So in linear approximation, what is done there, you have several data points, right? You have several data points, and what you do there, for all this data point, you find the best fit line, right? What is the best fit line? It is just the linear approximation for all this data value given here. Okay, here this linear approximation is about a curve. Here it is about the data value. For this linear regression, you find the least square method. So that is a different method from linear algebra. But yeah, linear approximation means approximating with a line. That is what I'm trying to say. Okay, fine. Okay, so there were 3 topics I was telling. The first topic was steepest ascent or descent, and the second topic is tangent. Okay, and the next topic, the last topic of week 10 is critical points. Okay, what are critical points? First of all, in one variable, let us first revise. What are critical points? A point A is called a critical point of a function f of x if either f is not differentiable at a or f dash of a is equal to 0. Okay, there are 2 conditions, remember. F is either not differentiable at a or f dash of a is 0. Okay, if f is differentiable at a point a of a local extremum, it satisfies f dash of a is equal to 0. And so every point of the local extremum is a critical point. Okay, for example, what are local extremums in one variable case? For example, you see maybe this point here, it is a local maximum. And here, this is a local minimum. Okay, and here this is again a local as well as global. This for this, suppose you are, this is the range you are considering. This is the local minimum, or depending on what is the domain given to you, this is the global or local minimum. Okay, fine. So at these places, you know that what is the tangent line? All the tangent lines are going to be
parallel, so it's 0.
Parallel to the x-axis. Okay, tangents have slope 0 at the local extremal points. Okay, fine. Note, not every critical point is a point of local extremum. A saddle point is a critical point which is not a point of local extremum. Okay, first of all, what is a saddle? Literal meaning, not in mathematical sense. What is a saddle? Saddle of a horse. Yeah. So you have a horse where the rider sits. That is called a saddle, right? Yeah. So the shape is something. If you see it from the side, it is something like this, right? So this is the place where they sit. So why that is called a saddle point? Particularly in the 3D case, you can understand it better, because you see in this side from the, suppose this, I don't know how to draw a graph of a horse and the picture of horse and all. Let's say this is the side of the horse. Okay, so from the side direction, you are looking at this saddle, and now you see what is this point here. For example, this is the lowest point, right? Okay, now imagine the same saddle from the front side or the back side of the horse. Okay, so in that case, the position, the same point, it will be lying in this point of that particular saddle. The saddle will look like this. I'm not a very good person to draw this kind of things, but I want you to just maybe you can Google and see what is a saddle and understand from the figure there. Okay, the same point here from the front side of the horse or from the back side of the horse, you see this point is now kind of the highest point. Okay, so it is also lowest in one direction and also the highest in the other direction. Okay, so these points are called saddle points. They need not be local extremal points. Okay, I guess I have a better graph to show what is a saddle point. Yeah, look at this graph. Okay, look at this graph. In this graph, along this yellow curve, okay, along this yellow curve, this point here, it is kind of not a very minimal point or maximal point. Somewhere where the graph is kind of a constant, you see, or if it is kind of going down also, you can kind of, along this yellow line or the orange line, you can see that this is kind of the minimal point. Okay, but what happens along the blue line? This point,
it becomes the maximum one.
It is the maximum. So you see the same point, depending on the direction which you are considering, you can also imagine this as the saddle itself. Almost the saddle is also having a similar shape, the saddle of a horse. Okay, so depending on the direction in which you are looking at, this point may be the maximum or minimum. Okay, but it is neither the, in the case of, in the sense of mathematical way, this point is not a local extremum. That is why this is called a saddle point. Okay,
similar to point inflection points. It's like Will they be similar?
Sorry?
Are they similar to inflection points? Are they one and same, or like?
What are inflection points? Can you tell me the definition?
I think like here, like in x cube, the point 0, we call that inflection, where the curve changes the direction. Like,
Okay, so by the way, here you see that these points are critical points, but they are not local extrema or maxima. That's all. So if you want to compare it with something else, then we will do it at the end. Okay. Okay, so here you see you have the graph of f of x is equal to x cube. Now for this, at the point x is equal to 0, what is the slope? What is the tangent line? It is parallel to the x-axis, right? Now it means what? The derivative at this point, it is 0, right? But is this any local maximum or local minimum?
No.
No. So again, this is a saddle point. This is the example you see in the case of one variable case. Okay, in the one variable case, you consider this as a saddle point because you see it is neither a maximum nor neither local maximum nor local minimum, but it is a critical point. Okay, so these are called saddle points. Okay, fine. So now how to find local extrema or local minima? From for two variable, it is actually very easy. From the graph, you can at least approximately point where they are, right? But in the 3D, it is not that simple. Okay. So anyway, you know the definition of what are local extrema, right? So if you have a function with the domain D and suppose A is a point in the domain, then what is the local maximum? You should have f of x is less than or equal to f of A. F of A is the maximum value for f of x in a specific open ball. Okay. So in the case of one variable, you consider open interval, right? For local maxima or local minima, you contain an open interval. But when you come to multivariable functions, you consider an open ball. The analogous in the case of one variable is that you have open intervals in that case. That's all. Okay. For example, suppose you are having a function like this. Let us say you are having a function like this. Can this point be a local minimum? The domain is 0 to some A. Can this point be a local minimum? Do you remember
No,
or
right,
not?
ma'am.
It cannot be local minimum, right?
No, it has to be on the curve. It cannot be at the ending.
You
Right?
should have an open ball, right? You should have an
Mm-hmm.
open ball containing this point or open interval in the case of one variable. But that is not the case. That is why you see this point cannot be a local minimum. Okay, fine. So the same they are saying using the concept of open balls here. Okay, so exactly the opposite of maximum is the minimum. F of A is the smallest of all the f of x value inside this set B intersection D. Okay, so local extremum is a local maximum or local minimum. That's all. Okay, how to find this? If del f of A exists for a local extremum A, then del f of A is equal to 0. So if you know that a point A is a local extremum, then the gradient function at that point is 0. Okay, so a point A tilde is a critical point. So now we are coming to the definition of critical point for multivariable function. Exactly the same like we saw in one variable case. A point A is called a critical point of a function f of x tilde if either del f of A tilde does not exist or del f of A tilde exists and del f of A tilde is equal to 0. In the case of one variable, we see either the derivative exists or the derivative at that point is 0. Okay, either it does not exist or the derivative at the point is 0. So here instead of derivative, we are having the gradient function. That's all. Okay. So now for this function, critical points of f of x comma y, how do we find? Exactly, this is what we are going to do. We are going to calculate what is del f of x comma y. What is del f of x comma y? Can you say?
And so it will be 2x plus 6y plus 2 comma 6x plus 8y minus 4.
Okay. And you want to now equate this del f of x comma y equal to 0. So if you are equating it to the 0 vector, then what are the equations you are getting?
2x plus 6y plus 2 equal to 0. Okay, minus 2. 6x plus 8y equal to 4. Okay, and we have to solve for x and y, is it, ma'am?
Yeah, that's all.
Okay,
So you have the equation 1, equation 2. Let us now multiply the equation 1 with minus 3. So what is it you will get? Minus 6x minus 18y 6. So what is the answer you will get?
0 plus minus 2. Okay, y equal to 1.
So if y is equal to 1 and I am substituting it here, 2x plus 6 times of 1 is equal to
Y equal to minus 1.
okay. So what is the critical point for this function?
Minus 4 comma 1.
Ma'am, here y will be
Y
minus
is
1.
equal to minus 1.
Ma'am, I think there is a
Sorry, y is equal to minus 1. So here we'll also have minus 1. So plus 6. So plus 4. Thank you for
X
pointing.
equal to 2.
It's 4 and 2. So 2 comma minus 1. Thank you. Okay, fine. So I already explained saddle points. So saddle points, you see, it is a critical point where the gradient function does not exist. So the gradient value is 0, but your A tilde is neither a local maximum or local minimum. Okay, so you see that it is a critical point such that your gradient exists and it is equal to 0, but your A tilde is not a local extremum. I have already explained this two graphs already. So the saddle point concept is clear for you, right? Saddle point and finding critical points, is it clear for you? Okay. So now using the concept of critical point, the next thing is that how to find the absolute extrema. Okay, absolute or global extrema, how to find that. Okay, for absolute maximum or absolute minimum, instead of considering any open balls, you are considering the entire domain. That is the only difference between local extrema and absolute extrema. Okay, so in local extrema, you contain D intersection B, where B is an open ball. Okay, but in the absolute maxima case or absolute extrema case, you can entire D you consider. You consider entire D. Okay, this is the only difference between local and absolute. Okay, fine. For example, you consider this function x squared plus y squared. You see, obviously, this is a point of global minimum. Okay, also it is a local minimum in this case. And here you see for this function, here you have a local maximum. Sorry, global maximum. Okay, so here for this this function actually will keep on going. Does this have a global maximum, this function here? Does this have a global maximum?
No, it's open at the top. So
yeah, and for this, does this have a global minimum?
No.
Okay, so the global maximum or minimum may or may not exist. Okay, so when do they exist then? What is the condition under which the absolute maximum or minimum exists? A domain D in Rn is called closed if it contains all its boundary points. For example, in the what is closed interval? If it contains its boundary points, right? So if you have an interval a comma b, and you take this closed version, these are the boundary points, right? For the this interval case, right? So if these endpoints are contained, then you call it closed interval. The same concept is there in Rn also. Okay, a domain D in Rn is called closed if it contains all its boundary points. I'm roughly speaking here so that you can understand. Okay, a domain D in Rn is called bounded if it is contained inside a open ball around 0 with finite radius. Okay, so for example, in the case of interval, you take any interval a comma b. Okay, and when do you say it to be bounded? You take 0 comma maximum of either mod a or mod b. So whichever is maximum, you take maximum of a comma b plus some epsilon, and then here maximum of a comma b minus epsilon, minus maximum. Okay, that is going to give you the interval which contains this interval a comma b. Okay, same way, if what is bounded sets in the Rn, you can consider consider any open ball with the centered origin and finite radius. Okay, so you know what is closed and bounded now. Okay, so there is some fact given here. If the domain D is closed and bounded and F is continuous on D, then the global maximum and global minimum must exist. Okay, so exactly the same thing you see for one variable case also. If your domain is closed and bounded, then your F is continuous, and also your F is continuous in that domain, then there is a global maximum and minimum. Okay, for example, in this case we told that the global maximum does not exist. Why is that so? Here your domain is not bounded, right? Your z value is keep on increasing, x, y, everything is increasing. It is not bounded. The same is happening here also. It is not bounded. Okay, so note that the global maximum and minimum, or in particular local maxima or local minima, unless they are on the boundary points, just like I told you here. Okay, unless they are in the boundary points. Where was that? Yeah, so it is in the boundary point. So this is just a global minimum, not a local minimum, because it is a boundary point. Okay, fine. Okay, what are the steps to find the absolute extrema? Exactly the same similar steps you see in the case of one variable. First of all, find all the critical points that lie in the region D and determine the function values at each of these points. Find all extreme values or extreme of the function on the boundary. What in the extreme means, I will tell you with an example. Okay, the largest and smallest value found in the first two steps are the absolute minimum and maximum. When I do an example, it will be clear for you. Okay, let me do an example. Find the absolute maximum and minimum of this function f of x comma y over the square with vertices 0, 0, 2, 0, 2, 2, 0, 2. Okay, let us first draw this square. So you have 0, 0, and then 2, 0. So this is your 2, 2, and this is your 0, 2. So for this square, this is your domain now. This is the D you are considering. Now within this D, what are all the critical points? That is the first step for you. So first step is finding the critical points. How do you find the critical point?
Del f, del f equal to 0.
Yeah. So del f of x comma y. What is del f of x comma y here?
It would be 3x square minus 3 and 3y square minus 6y.
So if your del f of x comma y is equal to 0, comma 0, this is going to give you 3x squared minus 3 is equal to 0, and 3y squared minus 6y is equal to 0. So x squared is equal to 1, and here 3 times of y into y minus 2 equal to 0. So this will give you y equal to 0 or y is equal to 2. Okay, and here this will give you x is equal to plus or minus 1. Okay, but is minus 1, if you are taking the value x is equal to minus 1, is this falling inside the domain?
No, ma'am.
No. So it means you can consider only 1, comma 0, and what is the other value? 1, comma 2. These are the two possible values you can consider.
So we have to draw a graph, is it, ma'am? Like
not necessary. No. If you want to
right.
visualize, maybe you can use some 3D calculator and look at the graph, but it is not required. This is your 1, comma 0 and your 1, comma 2.
And also in the case of 1, comma 2, ma'am, the given intervals are open intervals, right? So
they are not intervals. Please, they are not intervals. They are vertices.
Just points. Oh, okay, they are just points. Okay, fine.
Okay.
Yeah.
Fine. So also remember what is there in step 1. Determine the function value at each of these points. So let us find the function value at each of this point. What is now f of 1, comma 0?
Ma'am, that is not the point for 1 comma 0, right? In the graph.
Oh, sorry. Sorry. I don't know why I put this one. Sorry. So your 1 comma 0 is here. Sorry.
You started there, ma'am, one, and then you just
1 comma 2 also, ma'am. Yeah.
1 comma 2 is
1
there
comma
only.
2 is fine, I guess.
Yeah, yes, ma'am. Yes, ma'am.
Yeah. Okay. So, okay. Here you have what is f of 1 comma 0 now. This is your function. What is f of 1 comma 0?
1 minus 3 plus 1.
1 minus 3 plus 1, which is minus 1. And what is f of 1 comma 2?
1
Ma'am, minus
plus
3.
minus.
Ma'am, no, the
yeah,
1 comma 0 I'm saying.
it is
Minus
same.
5.
1
Minus
plus 8 minus 3 minus 12 plus 1, right?
minus 5.
Okay. 9 minus 3, 6 minus 6. Yeah. Minus 5.
Minus
Thank
5.
you. So now the next step is that what happens in the boundary. So what are all the boundary? First you need to see that. Now what is this boundary? How can we write this boundary representation? We are going to see. How do you represent this particular boundary? Here what is the value of x?
2.
And what are the values of y?
0 and
0 to 2.
It is 0 less equal to y less equal to 2. Okay. Same way, what about this particular boundary? Here x is equal to
0
and your y values are varying from
0 to
0
10.
to 2. Okay. And what about this boundary here?
Y will be equal to 0.
Y is 0 and your x is
X
varying
varies
from
0 to 2.
0 to 2. Okay. And what about this boundary here?
Y will be equal to 2 and x varies from 0 to 2.
Y is equal to 2 and x varies from 0 to 2. So we have to see now what happens in these different boundaries. Okay. So let us give some numbers 1, 2, 3 and 4. And all these 4 boundaries we are going to check. Okay. So in the first case, x is equal to 2, 0 less equal to y less equal to 2. So your f of x comma y, you can write it as f of 2 comma y. Now what is f of 2 comma y? For this function, what is your function? X cube plus y cube. Let me maybe write this. X cube plus y cube minus 3x minus 3y squared plus 1. Now for this function, what is f of 2 comma y?
8 plus
8
y
plus
cube
y cube minus
minus 6
minus 3y squared plus 1,
plus
which is y cube minus 3y
plus 3
squared plus
plus 3.
3. Right? Now for this, you are now having this function. Now for this function, what are the critical values? What are the critical values for this function now? F dash of, with respect to y only it is varying, right? So with respect to y, maybe I give some other name. F1 of F1 I give the name F1 of 2 comma y. So what is this function now?
3y
3y
square
squared
minus 6y
6y. If
equal
I'm
to 0.
equating it to 0, what are the y values I'm getting here? Y
3y
into y minus 2 equal to 0. So you get y is equal to 0 and y is equal to 2. Already we know the x value. So it is 2 comma 0 and 2 comma 2. Right?
Yeah.
2 comma 0 and 2 comma 2. Okay.
3y into y minus 2.
Sorry?
3y into y minus 2.
Where?
The other side, ma'am.
3y?
Yeah, I was saying in the next step.
Okay, next step. So here the second step, x is equal, okay, here you need to evaluate the function values. What is f of 2 comma 0? This is your f of x comma y. What is your f of 2 comma 0? 8 minus 6 plus 1.
3.
3. And what is f of 2 comma 2?
8
What is
plus
f of 2
8,
comma 2?
8 plus
8
8
plus
minus
8,
6.
16
minus 1.
minus 12 plus 1.
Mm.
So 16 minus 6, 10, 10 minus 12, minus 2, minus 1, right? It is minus 1, right? Yeah? Okay. Now, what is the second part we need to consider? X is equal to 0, 0 less equal to y less equal to 2. Now, what is your f of 0 comma y? It is y cube minus 3y square plus
Plus
1.
1.
So, you see, again, you are going to get the same part.
Yeah, that would be same.
The same thing you are going to get here. So I am just skipping this part. And but one thing here, you are getting y is equal to 0, y is equal to 2. But what is your x value? 0.
0.
Right? So you have the point 0, 0 and
0 comma
0
2.
comma 2. Now what is f of 0 comma 0?
1.
It is 1.
1.
And what is f of 0 comma 2?
3.
F of
Sorry.
0 comma 2 is
Minus
0,
3.
0 here.
8 minus
8
Minus
minus
3.
12.
Minus
12 plus 1.
sorry, not 6, minus 12, minus
Plus
4
1.
plus 1, minus 3. Correct? It's minus 3, right?
Yes, ma'am.
Yeah.
Yes.
Oh. Okay. And then for the third one, you have y is equal to 0 and 0 less equal to x less equal to 2. So what happens to your f of x comma 0? It is x cube minus 3x plus 1. So what is your, let's say this is f3. f3 dash of x,
3x
3x
square
squared
minus
minus 3. So again here you get x is equal to
Plus minus 1.
plus minus 1. So this case we have already seen, right? Or y is equal to, yeah, this case we have already considered. 1 comma 0 is already considered. So we don't have to evaluate it again. So here only x is equal to 1 case will come. So 1 comma 0 will have, then that we have already evaluated. F of 1 comma 0 is minus 1 is already evaluated. Okay. And what about the fourth case? Y is equal to 2, 0 less equal to x less equal to 2. And what is your x comma 2? The function I have written here, right? Yeah. So x cube
x
minus
plus 8.
3x plus 8 minus 12 plus 1, which is x cube minus 3x minus 3. Right? Now again you are going to get the same derivative and the same x value. X is equal to 1. So you have f of 1 comma 2. Again that 1 comma 2 I guess I have computed here, which is minus 5. Okay. So now what is the final step? So this is your step 2. So what is your step 3 then? You just look at the maximum and minimum values of all the computed values. What are all the points? First let us list down. 1, 0, 1 comma 2. What is the value of 1, 0? Minus 1. 1 comma 2 minus 5. And then we had these points here. F of 2 comma 0 is 3. F of 2 comma 2 is minus 1. And then f of 0 comma 0 is 1. F of 0 comma 2 is minus 3. So these values here. And then these values here. And then these values from here. Okay, these are the values I have considered for step 3. Now, can you tell me what are the values contributing to the absolute maximum and minimum? What is the least value?
Minus 5.
Minus 5.
So this is your absolute minimum. And what is absolute maximum?
3.
Yeah. So at this point, you have the absolute
Like it's there at 2 points, right?
The value at is -5, and at the point 2 comma 0 you have the absolute maximum, which is 3.
Also
Okay.
at 0,2 it's 3, right?
Yeah.
Yeah, then you have absolute maximum at 2 points.
Okay.
Okay, there can be several points, in fact infinitely many points where you can have absolute maximum. What is the immediate function you can give for example for this in case of one variable at least?
Sine, base,
Sine cos
cosine.
theta
Sine
cos
and
theta.
cos, right? Sine and cos you have at almost every 2 pi not almost, on all the 2 pi interval you have either the absolute maximum or absolute minimum. For example, in the cos case you have 0, 2 pi, 4 pi, all these cases you have absolute maximum, right? And or you have pi, 3 pi, all these cases you have absolute minimum, right? So function can have infinitely many absolute maximum and absolute minimum. Okay, fine. Okay,
And
so the
the
next
remaining
problem is quite similar. I will just give you the outline. Maybe the calculation part I will leave it to you, but I will give you the outline of how to do it. It is almost a similar problem only. Okay, now your f of x comma y is this function. Okay, and you are asked to
ma'am,
find, yeah.
just before going to the next problem, can you just scroll up a minute, like this question? Did we find saddle point, ma'am?
That is not required. It is not one of the steps
Okay, it
here,
was
right?
not asked. Okay, fine. Yeah.
Okay. Okay, fine. I particularly took this example because the visualization was provided. That's why I took this example. So before even finding the absolute maximum and minimum, let us look at this graph of the function. Okay, your x value is varying from -1 to 1, and y value is also varying from -1 to 1. Okay, so now just by looking at the graph, which points do you think are the absolute maximum? Do you think these 2 points? Yeah.
Yeah, they look like that.
It kind of
-1.
looks like the highest points on this graph, right? So it is x value is 1 and y value is -1. Okay, so it is 1 comma -1. Again, this point x value is also -1 and y value is also -1. So it is -1 comma -1. Okay, and which point you think is the minimum point? Kind of somewhere in the middle of this, right?
0.
Somewhere in this middle, which is nothing but the point 0 comma 0. Okay, this is the guess and visualization of this absolute maximum and minimum. Since the graph is given, I told you I will give you an outline of how to do the derivation for this and verify whether these are the actual answers. Okay, so exactly same technique. So what is the domain given to you now? What is your D? Now you are having a different triangle.
Rectangle.
What are the coordinates you are going to consider?
-1 to
-1 to 1 for x value, and again -1 to 1 for y as well. So okay, so this is the square you are considering. Now for this square, now what does this boundary, how can you write this boundary line? What is the value of x along this boundary line?
1, y from -1 to
Your
1.
x is equal to 1 and y varies from,
-1 to 1.
and here your x is equal to
-1, y minus
-1 and your y varies from -1 to 1. And here what is the value of y?
1, and x varies from -1.
And x value varies from -1 to 1. And here y is -1 and your x values varies from -1 to 1. Okay, the steps are as usual. So the first step, you find the gradient, okay, and equate it to 0. Find critical points, okay, and evaluate the function at those points. Second step, you consider each of these equations. Let's say 1, 2, 3, and 4. not equations, each of these boundary sides. So in all these boundary sides, 1, 2, 3, 4, for each of these 4, do the exact same steps which we did. You find again the critical points. Okay, and then and finally compare the evaluated values, evaluated function values. Okay, these steps are clear to you from the previous problem, right? What you have to do is clear for you, all right? Yes or no? Is it clear? Okay, fine. So what are the things we have seen so far in today's session? We saw first what is steepest descent and ascent and steepest descent. For that we used directional derivatives. Okay, so for directional derivatives, the only one table is required for the calculation of that. This is the table. So if you can take u in this direction, it is steepest descent, u in this direction, steepest descent, and if it is orthogonal to del f, then no change. Okay, and then the next concept, tangent. For tangent, you have mainly two formulas. So one is the equation of the tangent given by this. Okay, and also you have the equation of the tangent plane, which is given by this. Okay, these are the two main formulas which we have used for tangents, and exactly the same formula is there for linear approximation as well. So nothing new for linear approximation. And then when you come to critical points, so for finding critical points, you evaluate del f of a tilde and equate it to 0. Okay, and then what are saddle points? You should know the meaning of what are saddle points. They are critical points but are not local extrema. Okay,
Do
and
we have to check for saddle points, like if we have to check like if a point is a saddle point or not?
okay, in that case, if the graphs visualization is given, you can do it. Otherwise, the specific technique for which you can verify the saddle points is not covered here. Okay, fine. And absolute finding the absolute extrema, here the steps are given to you. Okay, here this step maybe you can use for the saddle point also. You see whether it is a critical point and whether it is a absolute extrema, that whether the point is an absolute extrema or not, you can check. For example, you see that maybe here this 1, 0. Okay, it is a critical point, but is this an absolute maximum or minimum?
No, so
No, right? So can you say that this is saddle point? Yes, right?
But
Okay.
it works even if it's a local maximum, that it won't be a saddle point, right?
Oh, I told with absolute maximum. Sorry. Okay, it is for local maximum. Yeah, fine. Fine. So in that case, you need the graph of that function. Here you can say that only it is not a global extrema, but local extrema is not covered here. Yeah, for the steps involving absolute extrema, you have these steps. First, find the critical points and then evaluate the function values at these points, and then you look at the boundary values and find the critical values at these points, and then look at the largest and smallest values found in step 1 and step 2. Okay, that gives you the absolute extrema values. Okay, so these are the topics for week 10. Okay, I hope these topics are clear. By the way, some students asked for the explanation part or the derivation part for what is that tangent plane or tangent plane only you asked, right?
Tangent line.
Tangent line. Okay, fine. So for the tangent plane derivation part, in the next session PDF itself, I will attach that tangent line derivation. Okay, since it is already late today, so I will add the derivation in the next session PDF. If you have doubts, we will discuss it in the next Sunday session again. Okay, please remind me if you have doubts. Please remind me in the Sunday session, next Sunday session.
Okay, and just one doubt.